Assalamualaikum, my name is Najwa binti Muhammad Razi. Matrix number CP190077. We are given this task entitled Introduction and Definition to Soil. Before I proceed, I'm going to show you some examples of soil failure that can cause sinking, consolidation, and also liquefaction to the building. For further explanation, I'm going to give the definition of soil. The engineering describes soil as the solid material that can be removed without blasting. A soil may be defined as all naturally occurring, loose, uncemented, weakly cemented, relatively unconsolidated mineral particles, organic or inorganic, in character laying over the bedrock, which is formed by weathering of rocks. There are many ways we use soil. From use and observation, we can define our soil. In actuality, it's not our definition of what soil that makes soil. It is many other physical, chemical, biological processes on our earth that make soil what it is. Alright, so now we go to the weathering of rock. Weathering is the mechanical breakdown of rock and associated chemical alteration of mineral that occurs at the earth's surface. Weathering is the process where rock layer is dissolved, worn away, or broken down into smaller and smaller pieces. There are mechanical, chemical, and organic weathering processes. 3 roots breaking up bedrock. Organic weathering happens when plants break up rocks with their growing roots, or plant acid help dissolve rock. Once the rock has been weakened and broken up by weathering, is ready for erosion. Erosion happens when rocks and sediments are picked up and moved to another place by ice, water, wind, or gravity. Flat benches called as terrace form as the river eroded layers of mud and ash. Mechanical weathering physical breaks up rocks. One example is called frost action or frost shattering. Water gets into cracks and joins in the bedrock. When the water freezes, it expands and the cracks are opened a little wider. Over time, pieces of rock can split off rock face and big boulders are broken into smaller rocks and gravel. This process can also break up bricks on buildings. Rainwater is a very weak acid. It can dissolve limestone and other carbonate rocks, leaving behind pits and holes. Chemical weathering decomposes or decays rocks and minerals. An example of chemical weathering is water wheel dissolving limestone. When ice melts or wind and water wheel slow down, they cannot carry as much sediment. The sediment is dropped or deposited in landforms. Soil is a complex of mixture of detritus, loose rock fragments, coal, regolith, water, air, and organic material. I hope my definition is loud and clear. That's all from me. Thank you.
Hi, my name is Puri Jamling. So now I'm going to continue the presentation with formation of soil. Formation of soil is defined as the process by which soil is formed as a result of interactions over time between parental material, climate, topography, and organism. There are 2 major processes in formation of soil, which is slow chemical alteration by water seeping through the weathered rock material after rains, and second is mixing of the rock material with organic debris produced by the decay of plant. There are 4 processes of soil formation. First is accumulation of material. Materials are added to the soil, such as organic matter and decomposing material or new material deposited by the force of ice, water, or wind, and they accumulate over time. This happens in the top layer of the soil. In poorly drained soil, the organic material accumulates since waterlogging prevents it from being oxidized or broken down by soil organisms. Second is leaching and losses. Through the movement of water, wind, ice, or the uptake of the accumulated material by plant, the new particles including clay, organic matter, clay, silt, or other chemical compounds are leached and eroded away or taken up from the soil by plant. And the third one is transformation and elevation. Here the soil particle held in the suspension after the leaching, such as clay, are transformed, after which they accumulate. Transformation is the chemical weathering of silt, sand, and the formation of clay mineral, as well as the change of organic material into decay-resistant organic matter. And the last one is podsolization and translocation. Podsolization takes place when strong acidic solution break down the clay mineral. Accordingly, aluminium, silica, and iron from complex material through with organic compound in the soil. These material at the accumulation are translocated within the profile and between the horizon. After a relatively extended time, the movement of the accumulated mineral precipitate, such as iron oxide mineral, are responsible for the reddish and brownish color of the different soil horizon. So now let's talk about the factors that affect soil formation. First is time. Soil formation takes several hundred of thousands of years to undergo significant change and the eventual formation. Most of the soil of the world have taken more than 10,000 years to form the current state of soil. Second is parental material. Parental materials are the unconsolidated organic deposit and minerals in which soils are developing. For this reason, parental material determines the mineralogical composition and widely contribute to the chemical and physical characteristics of the soil. And lastly is climate. Climate, especially precipitation, temperature, and frost action, have a fundamental influence on the soil formation process that take place within any given location. The prevailing climate condition highly determine the nature of weathering process that will take place and the rate of physical and chemical processes. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Nasira binti Mayudi. So next, I will continue with types of soil. Soil has three examples of state: solid soil, soil with air in the pores, and soil with water in the pores. Due to the number of different forms of organic and mineral composition, there are various types of soil that undergoes different environmental pressure. First, clay soil. Clay is one of the many types of soil that are distinguished as soil in which particles are packed tightly together with each other with little or no air space. Because of this characteristic, clay is the densest and heaviest type of soil. Defining factors of this soil are fine particles, smooth when dry, sticky when wet, retains water, drains poorly, less space to let air pass, rich in nutrition, and lastly, cool and dense. The ideal crops for this soil are leafy vegetables, peas, tomatoes, and peppers. Next, silty soil. Silty soil is extremely smooth, and since it retains plenty of water, it is fertile. Despite the good characteristic of this kind of soil, it lacks nutrition compared to other types of soil. Silty soil is ideal for agriculture use as the particles in silty soil are minuscule. Defining factors for this soil are tiny particles, slippery when wet, not grainy or rocky, extremely fertile, retains water, easily transported by wind and water, good for agriculture purpose, and easily compacted. The ideal crops for this soil are all vegetables and fruits. Next, sandy soil. Sandy soil are one of the worst types of soil to grow any kind of plants in. This is because sandy soil has one of the largest particles and that prevent the soil from retaining water, making it hard for the roots of plants to establish. Defining factors for this soil are large particle, dry and gritty to touch, easily drain water, less water retention, warm and airy, even when wet, easily scrambled through the fingers, and lastly, lack essential nutrition. The ideal crop for this type of soil are watermelons, peanuts, peach, tulips, cistus, and hibiscus. Next, loamy soil. Loamy soil is one of the perfect types of soil because it is mix of sand, clay, silt, and even some humus. The pH level of loamy soil is 6 with high calcium and level. The specific composition of loamy soil can vary, but with the right balance of additive, it can be made ideal. Defining factors of this type of soil are well-drained, fertile, mixture of sand, silt, and clay, retain water, retain nutrition, strong granular structure, soft and crumbly, easy to work with, and well aerated. An ideal crops for this type of soil are tomatoes, carrot, parsnips, tomatoes, roses, amaryllis, marigold, and zinnias. Next, we go to chalky soil. This kind of soil are found in limestone bed that have chalk deposit that are deep. This is not an ideal soil for growing plants because it can be hard to work with. Chalky soil is alkali and cause yellow and stunted plants. Defining factors for this type of soil are lime-rich soil, stony, severely dry in summer, poor in nutrition, warm quickly in summer, pores, high alkaline, and lastly, free draining. The ideal plants for this type of soil are honeysuckle, jasminum, roses, and geranium. And lastly, we go to peaty soil. The soil has a lot of organic material and is rich in water, which make it one of the best type of soil for plants. But the soil need to be drained first. Because of high water and nutrition content, peaty soil keeps plants healthy even in dry weather. The acidic water content is good for controlling plant disease and can be used to balance the pH level of other kinds of soil. Defined factors for this soil are dark brown in color, soft and spongy to the touch, contain acidic water, rich in organic matter, retains water, store nutrition, improve soil buffering, well aerated, found in bogs, and lastly mixed in soil to improve structure. The ideal plant for this type of soil are sphagnum moss, irrigation scrub, and sedges. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Naufatin Syafiqah binti Muhammad Zamshah. Okay, today I'm going to present about phase relation. Okay, phase relation has two types. There is 3-phase system and 2-phase system. For 3-phase system, we call it partial, and for 2-phase system, we call it dry or wet system. Okay, next is 3-phase diagram. This is 3-phase diagram which contain air, water, and solid. Next is 2-phase. That is fully saturated soil. Okay, it contains water and solid or soil. Next is 2-phase for dry soil. It only contain air and solid. Okay, next this is the figure of phase diagram. Okay, next is phase diagram in terms of weight. Okay, for volume, Vs means volume of solid, Vw means volume of water, Va volume of air, Vv volume of void, and Vt total volume of soil. Okay, for weight, Ws is weight of soil, Ww weight of water, Wa is weight of air, and Wv weight of void, and Wt is total weight of soil. And next is for phase diagram in terms of mass. Okay, Ms is mass of solid, Mw mass of water, Ma mass of air, and Mt is total mass of soil. For weight relationship, we have water content. Water content is a measure of the water present in the soil. To calculate the water content, we divide mass of water with mass of soil, and time by 100%. The answer must express as percentage. The range equal to 0 minus 100 plus percent. Okay, next is degree of saturation. The degree of saturation is the percentage of void volume filled by water. To calculate the degree of saturation, we take total volume of void contain water divide by total volume of void and times by 100%. Range 0 to 100% for dry and saturated. Next is void ratio. Okay, void ratio is a measure of void volume. Okay, to calculate the void ratio, we take volume of void divided by volume of solid. Next is porosity. Porosity is also a measure of void volume. The answer is expressed as a percentage. Okay, we take volume of void divided by total volume of soil sample, and it also times by 100%. The theoretical range is 0 to 100%. Okay, this is a relationship between porosity and void ratio. To get void ratio, volume of porosity divide 1 and minus value of porosity, or we can calculate value of void ratio by divide 1 and plus value of void ratio. Next is air content. Air content is a ratio of volume of air void to the volume of void. Okay, to get air content, we divide volume of air with total volume of soil. Next is specified volume. To get specified volume, we calculate 1 plus void ratio. Okay, next density. Density is density of soil in the current state. Like to calculate density, we take total mass of soil and water divide by total volume of soil and volume of void. For specific gravity, specific gravity is ratio of weight of a given volume of soil at a given temperature to weight of an equal volume of distilled water at the temperature. Okay, both weight being taken in air. To calculate the specific gravity, we can use weight of a substance divided by weight of an equal volume of water, or we can use unit weight of a substance divided by unit weight of water. Next is degree of saturation. Okay, degree saturation, we take WGS is the density of water. We divide by ratio. If the volume of solid is 1 unit, then volume of air void is E unit. Okay, next is degree of saturation. When degree of saturation equal to 1, it will be void ratio equal to density of water. For air contained, void ratio minus density of water and divide by 1 plus void ratio, or porosity multiplied by 1 minus degree of saturation. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Nurul Afifi binti Kamarazan and my metric number is CP190005. I will continue with my part. Okay, my part is weight, mass in volume relation. First, bulk density, PM, is the density of the soil in the current state. PM equal to MT over VT, which is MT is total of mass and over total of void. There are unit in T or meter cube or G or milliliter or kg or in meter cube. Then weight, mass, which is volume relation. First, saturated density, Psat, is the density of the soil when the voids are filled with water. And submerged density, P prime, is the effective density of the soil when it's submerged. P prime equal to Psat minus Pw. Unit of solid equal to Ms over Vs. Dry density, Pd, is the density of the soil in dry state. Pd equal to Ms over Vt. There are unit in T, meter cube, G, milliliter or kg or meter cube. Soil unit weight, Kn or meter cube. First point, bulk or total unit weight, gamma equal Wt over Vt. Dry unit weight, gamma D, weight of soil solid over total volume of soil equal Ws over Vt. Buoyant, which is submerged unit weight, gamma B equal to gamma minus gamma W. Soil density, kg or meter cube. First, bulk or total density, P equal to MT over Vt. Dry density, Pd, equal to Ms over Vt. Third, buoyant submerged density, Pb, equal to P minus Pw. Phase relations, consider a fraction of the soil where Vs equal to 1. Second, the other volumes can be obtained from the previous definitions. Third, the masses can be obtained from mass equal to density times volume. In the diagram, air, water, soil, there are Se in water at volume, and in the soil is 1, and E is air and water. In masses, in water, there are SEPW, in soil there are GSPW. From the previous definition, we have first W equal to MW over MS equal to SE over GS. Second, N equal to VV over VT equal to E over 1 plus E. Third, NA equal to NAC. Fourth, AS equal to 1 minus S. Then PM equal to MT over VT equal to GS plus SE over 1 plus E, PW. Then PSAT, which is saturated, equal to MT over VT equal to GS plus E over to 1 plus E, PW. Then PD equal to MS over VT equal to GS over 1 plus E, PW. Then gamma equal to WT over VT equal to GS plus SE over 1 plus E, gamma W. Then gamma D equal to WS over VT equal to GS over 1 plus E, gamma W. Then gamma submerged equal to gamma saturated minus gamma W equal to GS minus 1 over 1 plus E, gamma W. And last, relative density. It is a measure of the soil state of compactness and expressed as dr equal E max minus E over E max minus E min. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rizal bin Omar. My metric number is CP190074. I will explain about stress, effective stress and pore water pressure. So first of all, we must know about stress. Stress can be denoted as sigma equal to gamma times Z, which is gamma is the unit weight of soil, kilonewton per meter cube, and Z is equal to depth of thickness from ground surface. Right. The second one is total stress. Total stress is generated by the mass in the soil body calculated by sum up of the unit weight of all the material, soil solid plus water, multiplied by soil thickness or depth. It also denoted as sigma, sigma V or PO, where Z is the depth of the point. So for pore water pressure, micro is equal to gamma W times HW, which is gamma W is equal to unit weight of water, which is 9.81 kilonewton per meter cube, or equivalent to 10 kilonewton per meter cube, while HW is depth below water table or overlying water surface. So, below the water table, the pore pressure are positive. In dry soil, pore pressure is 0. But above the water table, even the soil is saturated, the pore pressure will be negative too. So, how we want to calculate the effective stress? Effective stress, sigma prime is equal to sigma minus micro. Sigma is the stress and micro is the pore water pressure. So, we have to subtract sigma with micro. It is applied to saturated soil and has a relationship with two types of stress, for example, total stress and pore water pressure. So that's all for our presentation for introduction to soil. Thank you so much.